So a question that we might be forming at this point is, why is calculus concerned with finding slopes of these tangent lines or their equations? What's really the point? And actually, there are some interesting ideas related to concepts in physics that deal with these ideas specifically. And we'll talk about those here. They have to deal with motion of objects. Suppose that an object moves in a straight line according to the equation modeled by the following. So there's some equation that tells me kind of like where an object is. So you plug in a t, it tells me where the object is located at that time t. So this function would be commonly called a position function of the object. It tells me its location. For some reason, we often use s to stand for the position of an object. That's kind of weird, right? Because you'd think, why wouldn't this be p, or write this as p of t or something? I don't know, s is pretty standard. However, what we can start to do if we have a function like this is to talk about two different types of ideas. We can talk about what we call average velocity of an object over the time interval. So imagine maybe like a car in motion, right? Like maybe you're going to go out, you're going to drive to a store or something like that, right? The average velocity of your car over the time interval from maybe say the start to the finish of the trip is actually just needs to be calculated by how far did you actually travel and how long did it take you. But that is actually a slope. We can compute that by dealing with outputs of our function being subtracted and then the inputs of our function being subtracted. We can also talk about what we call an instantaneous velocity. And I'm color coding these very purposefully because an instantaneous velocity is actually going to be the velocity of the object, or you could imagine like the speed of your car at exactly a fixed moment in time. And that corresponds to the slope of a tangent line, which is why it's represented here with the limit definition that we saw up above. So this is kind of a really, really interesting idea that we end up with. This part here represents the slope of a secant line, whereas this part down here represents the slope of a tangent line. So let's see how we would actually use this in a particular example. So let's take a look here at example number 5. Suppose a delivery man drives on a straight line away from the depot to make deliveries. Okay, so you can imagine a little picture, right? Like here's the building, right? There's the depot, and you get a little truck. This is me sketching out an awesome truck, right? It's got some wheels, boom, right? And it's moving out to make some deliveries, right? So he drives over here, and then maybe at some point he drives back, and maybe there's houses and stuff along the way. So the function s of t, let's say that computes the total distance away he is from the depot. Okay, s is measured, measuring that distance is measured in miles. T is measured in how long this person's been driving. Okay? So what I'm going to be interested in doing is finding the average velocity of the truck from 2 hours to 3 hours. So that is from the second hour that he's been driving to the third hour. In that 1 hour period, can I calculate his average speed if all I know is where he's located? Well, actually, this is a surprisingly easy thing to do, because if I take a look here at kind of a rough picture of what this function of position looks like, I can see that I have something kind of like this. Right? I know this is a quadratic function. I know it opens upwards, got a positive leading coefficient. So I have some picture maybe like this. And I'm interested in looking on the interval from, say, 2 to 3. Okay, picture not to scale, but let's suppose that that corresponds to this. If I'm interested in the average velocity between these 2 points, then that means I kind of want to find the slope of this corresponding secant line that would be connecting here. Now that's unbelievably easy to calculate because that average velocity is just that slope, and we know how to calculate slope. So notice here, I could say that the slope of the secant line corresponds to my average velocity. So that would be the slope of my secant line. And I can easily get that by just doing, well, s of 3 minus s of 2 over 3 minus 2. Change in y over change in x, or in this case, change in s over change in t if you work with the appropriate variables. So this is really easy. If you compute the top, I'll compute the bottom, division of labor. Here we go. I got 1. Okay, so you should be able to kind of crunch out the top here a little bit. Let's see. We could easily see here that if I plug in the value of 3, I got to a value of 121. If I plug in the value of 2, I get 51. So this here equates out to be, I think, a total of 70, and that would be in units, miles per hour. So, holy crap, okay, so this guy is flying at 70 miles per hour average speed. Hopefully this isn't through like subdivisions or small back roads. Okay, so I can calculate, though, this average velocity pretty simply. But what if I wanted to know something even more specific? What if I wanted an instantaneous velocity? What if I said, at exactly the moment of 2 hours, I want to know, what does the speedometer in the truck read? What is the velocity at exactly the instant of the 2-hour mark? Well, that is the slope of a tangent line. And in order to find that, I would need to go ahead and calculate that big limit. So I would be looking for the velocity at time 2, the speed at time 2. Speed and velocity, I know, are technically different, but for the moment, we'll consider them the same. So in order to do this, remember, I'd have to compute the limit of the same sort of setup. I'd be interested in doing s of 2 plus h. 2 is where I want the velocity. And then I would be thinking about, okay, well, if I imagined at 2 and another point over here, I could imagine sliding that 1 point back or letting the gap between the points disappear. I can slide the red dots together to create the slope of the blue dot. That's all, again, we're setting up here. Now, to figure out what this would look like, well, let's see. All right, so I'm going to have to go and set this up. This is going to probably be a little bit ugly. Let's see, so I have to plug 2 plus h in for all of the t's in here. So I'd have 1 minus 5, 2 plus h, plus 15, 2 plus h all squared, and then minus, and remember, I'll have to kind of group these things here together. I want to make sure I'm subtracting everything from s with a 2 plugged in. And, oh, wait a minute. Didn't we already do s with the 2 plugged in up here? That's just going to be 51. Okay, no big deal. All right, so let's see what we come up with when we actually try to simplify this down. All right, I'm going to go ahead and simplify my numerator as much as possible here. So I'm going to get 1 minus 10 minus 5h, right? So that's what I get when I distribute here. Then I'm going to get 15 times, and I have to multiply out this quantity. So let's see, I'm going to get 4 plus 4h plus h squared. Hopefully you can confirm that is indeed what you get. And I still have my minus 51 up there. Okay. Let's keep simplifying a little bit. I can now maybe go ahead and distribute that 15. So I'm going to get 1 minus 10 minus 5h. If I distribute the 15, I'm going to get plus 60, then plus 60 h's, and then plus 15h squareds, and I still have minus 51. Okay, so let's go ahead and try to simplify this down as much as we can. Let's start by maybe taking a look at the constants that we're going to be left with. So constants. Okay, so let's see. We have 1 minus 10, so that's minus 9. 60 minus 9 is 51. 51 minus 51, 0. Okay. Oh, great. Okay, so we're just left with 0 on that. Minus 5h plus 60h. That's 55 h's. And then we have 15h squared. I guess I can make my fraction bar here a little bit shorter. And we're just over h. Notice, can I compute the limit yet? No, but it wouldn't be too much work to go ahead and simplify out an h from top and bottom. I'm going to tackle this in one step. You can imagine factoring out an h from the top and then canceling out with the bottom. And if you did that, you'd be left with 55 plus 15h. But if h is going to 0, I can direct substitute in here, and I'm going to get 55 plus 15 times 0, which is just going to end up being 55 miles per hour. Notice what that means is that at exactly the 2-hour mark, what does the speedometer in the truck read? 55. That's what it is. So this becomes a really cool idea that we can actually track the motion of items. If we just know a way to calculate where they're located, we can figure out their average velocity and their exact velocity at an instant at any point along the trip. And that's a really, really powerful set of ideas.